Early in the 19th century, the farthermost planet known in the solar system was Uranus. The first planet to be discovered beyond Uranus in 1846 was named Neptune. In 1930, what seemed to be a planet beyond Neptune was discovered and was named Pluto. During this time, the heaviest element known was uranium. Appropriately enough, the first transuranic element to be discovered was named Neptunium, and the second transuranic element was named Plutonium. Neptunium is produced when a neutron is absorbed by a U-238 nucleus, becoming U-239. Rather than undergoing fission, this nucleus emits a beta particle and becomes Neptunium-239, the first synthetic element beyond uranium. The half-life, capital T, of this isotope of Neptunium is only 2.3 days, so it isn't around very long. Neptunium-239 is a beta emitter and very soon becomes plutonium, in particular the isotope plutonium-239. The half-life of this plutonium isotope is about 24,000 years, so it lasts a considerable time. The nucleus of plutonium-239, like U-235, will undergo fission when it captures a neutron. Whereas the separation of fissionable U-235 from uranium metal is a very difficult process, because U-235 and U-238 have the same chemistry and nearly the same mass, the separation of plutonium from uranium metal is relatively easy. This is because plutonium is an element distinct from uranium, with its own chemical properties. Enough plutonium-239 was separated in World War II to provide the core of the bomb dropped on Nagasaki. The element plutonium is chemically poisonous in the same sense as are lead and arsenic. It attacks the nervous system and can cause paralysis. Death can follow after a sufficiently large dose. Fortunately, plutonium does not remain in its elemental form for long, because it rapidly combines with oxygen to form plutonium oxide and plutonium dioxide, PuO and PuO2. These plutonium compounds are undissolvable in water or biological systems, so if you eat or drink these compounds, they won't attack your nervous system, and for the most part, they're chemically harmless. But breathing them is another story. Plutonium in any form is radioactively toxic. It is more toxic than uranium, although less toxic than radium. Plutonium emits high-energy alpha particles which kill cells rather than simply disrupting them and leading to mutations. Interestingly, damaged cells rather than dead cells contribute to cancer. This is why plutonium ranks relatively low as a cancer-producing substance. The greatest danger that plutonium presents to humans is its potential use in nuclear fission bombs. Its usefulness is in fission reactors, particularly breeder reactors. Let's talk about the breeding of plutonium. Breeding of fissionable plutonium occurs when small amounts of fissionable U-235 are mixed with U-238 in a reactor. Fissioning liberates neutrons that convert the relatively abundant non-fissionable U-238 to U-239. Which beta decays to become Neptunium-239, which, in turn, beta decays to fissionable plutonium, Plutonium-239, as I described earlier. So, in addition to the abundant energy produced, fission fuel is bred from relatively abundant U-238 in the process. Some breeding occurs in all fission reactors, but a breeder reactor is specifically designed to breed more fissionable fuel than is put into it. Using a breeder reactor is analogous to filling your car's gas tank with water, adding some gasoline, then driving the car and having more gasoline at the end of the trip than at the beginning. The basic principle of the breeder reactor is very attractive. After a few years of operation, a breeder reactor power plant can produce vast amounts of power while breeding twice as much fuel as it had in the beginning. The downside of breeder reactors is the enormous complexity of successful and safe operation. As with uranium reactors, there are different types of breeder reactors. The United States gave up on breeders in the 1980s, and only France, Germany, India, and China are still investing in them. Officials in these countries point out that supplies of naturally occurring U-235 are limited. At present rates of consumption, all natural sources of U-235 may be depleted within a century. Countries then deciding to use breeder reactors may well find themselves digging up radioactive wastes they once buried. Many nuclear scientists do not think that deep burial is a desirable solution to the problem of nuclear waste. Devices are presently being studied that could, in principle, convert long-lived radioactive atoms of spent reactor fuel into short-lived or non-radioactive atoms. Nuclear wastes may not plague future generations indefinitely, as has been commonly thought. I want to leave you with two questions. Number one, more environmental radiation surrounds a typical coal-fired power plant than surrounds a fission power plant. What does this indicate about the shielding surrounding the two types of power plants? Number two, we have learned that when Neptunium-239 emits a beta particle, the Neptunium transmutes to plutonium. If Plutonium-239 emits a beta particle, what is the atomic number of the element it becomes? Until next time, good energy.